So let's see what are the different criteria which are used for scale up. Power input per unit volume. Now the basis of this scale up criteria is constant power input, which is equivalent to equivalent mass transfer rates. Constant impeller speed is another criteria, which is here given as NDI. This is the basis for constant shear. Now, the third criteria is constant volumetric oxygen transfer coefficient, which is defined as KLA. Now we already know about this. In order to ensure constant mass transfer characteristics in the vessel. Then, if we need to have constant mixing quality, then the basis is constant mixing factor, which is in turn a function of mixing time. Now, if constant pumping rate of the impeller per unit volume is found to be crucial and becomes the basis for scale up, which is given as Q by V, this would ensure constant liquid circulation rates in the vessel. Similarly, constant Reynolds number, this will be the basis for geometrically similar flow patterns at the two scales. So let's take these scale up criteria one by one and try to derive relationships between the different operating parameters at the two scales. So power consumption per unit volume is the first scale up criteria. If you do equality of power numbers and do the rearrangement, and then your di to the power of 5, if it can be broken up as di cube and di square separately. So we know that power number is P naught by n cube di to the power of 5, isn't it? And you have density. So this is your power number. So equality of power number is to be achieved. So then your P naught rho n cube di to the power of 5 at the prototype, which means is equal to P naught rho n cube di to the power of 5 at the model type. Density is the same, so it can be neglected, cancelled. So here, if you further have this as di cube into di square and do the rearrangement and make P naught di cube at the prototype here, bring it separately on the LHS, and here you have P naught di cube di square into di cube of the model type. So here is the model type, P naught by di cube. Remaining would be di prototype divided by di model type to the power of square. So square is brought together on the RHS, and your impeller speed at the prototype, it goes to the RHS to the impeller speed at the model type whole cube. So this is a rearrangement of the equality of power number. Now P naught by di cube, as I mentioned earlier, represents your power per unit volume for the geometrically similar vessels. Now this is the scale up criteria, which means at the prototype and the model type, we can consider further that these are same. So then if we keep this as a scale up criteria, then we can relate the impeller speeds at the two levels with the diameter of the impellers at the two scales. So the correlation between the two variables comes out to be Np by Nm to the cube is equal to dim by dip to the square. So we have rearranged this portion in this form given here as this equation. Let's take an example. If a 20-gallon fermenter is to be scaled up to 2500-gallon fermenter, then we know the scale ratio would be 5. The impeller speed of the prototype then can be determined. If P by V is the scale-up criteria, then in that case, we know now the diameter ratios can be given as 1 by 5. So therefore, your impeller speed at the prototype will become 0.34 times of the impeller speed at the model type to keep your power per unit volume constant at the two levels. So if you notice, the impeller speed in the prototype will be 1/3 of that in the model. However, for constant P0 by V, the NRE and the impeller tip speed cannot be the same for any given scale ratio. So by keeping your power number equality but compromising on the NRE, so your NRE will then be related as given here. Similarly, your tip speed, which is given as NDI, will also be related as shown here in equation 2. So your Reynolds number is what? It is rho NDI square by mu. Inertial force to viscous force. So this for prototype, we need to find a relationship of rho NDI square by mu at the model type. Your Nm by Np is equal to 1 by 0.34 and your dim by dip is equal to 5. So if you place this 1 by 5 the whole square and further divided by 0.34. So for constant P0 by V, the NRE and the impeller tip speed, you will see that they cannot be kept the same. So if this relationship holds for constant P0 by V as shown here between the NP and the NM, then the relationship between NRE at the prototype and at the model type will be shown here as equation 2 and as equation 3 for the tip speed. So NRE is what? Rho NDI square by mu. So let's call this for the prototype. And NRE for model type is rho NDI square by mu for the model type. Now mu and rho are the same. Now in terms of the prototype, if we divide this, so NRE at prototype to NRE at model type will become equal to NP by NM multiplied by DIP by DIM the whole square. NP by NM, if you notice, NP by NM, how were they related? For constant P0 by V was this. NP by NM is equal to 0.34. And your DIP by DIM is related by the scale factor of 5. So this is 25 times 0.34, which comes out to 8.5. So your NP, so we can say that the NRE at the prototype is 8.5 times the NRE at the model type. You can do similarly for the NDI, which is called the tip speed at the prototype, and here it is the tip speed at the model type. So tip speed at the prototype by tip speed at the model type, if you do, then we know that NP by NM is 0.34 and DIP by DIM is 5. This is the ratio of the tip speed at the prototype and the impeller tip speed at the model type. So if you need to find the relationship between them, this comes out to be 1.7 times tip speed at the model type will be your impeller tip speed at the prototype. This is what has been shown here in equation 3 and equation 2. So if we have a gas system, so right now the power per unit volume, the P0 was the ungassed power requirement. So if we have a gas system, will there be a variation in the correlation between the impeller speed and the diameter ratio? So there is an empirical relationship between the power consumption in gassed and non-gas system, which is shown here by equation, let's call it as equation 1, in terms of the impeller speed, in terms of the diameter of the impeller and the gas flow rate, volumetric gas flow rate. So the gassed power requirement to the ungassed power requirement is said to be proportional to these operating parameters. So if the gas power requirement per unit volume is the scale up criteria, which means PG. So the gas power requirement is being called as PG. The ungassed power requirement is P0 or P here, shown on the slide. So it is said that power per unit volume will be the scale up criteria, and from the previous equation, which we called as 1, we can relate the gas power requirement with the ungassed power requirement. So your gassed power requirement can be given as ungassed power requirement multiplied by this function involving the impeller speed, the diameter of the impeller and the volumetric gas flow rate. Now, if we go by power per unit volume, we can further have we can divide this equation here, both sides, by d cube. So rest is all constant, some scale factor. So constant. So the same equation 1 can be written as equation 2 as I have written here. Now this P by V and this PG by V, we know now this P by V can be given as in terms of the power number. So your power number was what? The power number is P0 ungassed power requirement by n cube d to the power of 5 into rho. Now again, this is a constant. So then your P naught by d cube from here can be replaced as NP multiplied by n cube times d square. So rho will get into the constant because it is a constant, and then this equation can be rewritten in the second line form, where we have replaced P naught by d cube as NP, which is your power number, d square, and rest of the factor is the same. So this will become NP times n cube. So this is what it is. So power number, this goes up here. So this is multiplied by the power number n cube d square, and we are keeping P naught by d cube on the RHS. So then your equation 1 can be rewritten in the form of equation 2 from the power number correlation. So now power number is constant. So then this can also get into the constant, and n when goes inside the brackets and d square also goes inside the brackets, they get added up, and the equation 2 can be written as equation 3. So now n will become 7 by 2 after addition, and d will become 7 by 2. I hope you can understand. So it is 3 plus 1 by 2 to the power of n, which is nothing but 7 by 2. Similarly, it has been done for d, where 3 by 2 plus square has been done. So this becomes again 7 by 2 inside bracket. So now, if for a gas system, power per unit volume is the scale up criteria, so then your gas power requirement per unit volume, which was the LHS here, is constant. So which would effectively mean that the entities in the bracket are nothing but constant at the two scales. So this will give us a correlation between the variables, the operating parameters at the two scales, which involves the impeller speed, the diameter of the impeller, and the volumetric gas flow rate. So this is how the operating parameters at the two scales can be related. Linear scale ratio is known. Then your impeller speeds at the two scales can be related by the equation shown here. Now let's take another scale-up criteria, which is volumetric mass transfer coefficient. If suppose the scale-up criteria being used is constant KLA, then for gassed systems, this volumetric mass transfer coefficient is related to power per unit volume and your superficial gas velocity in the form of empirical correlationship shown on the slide, where KLA is said to be related to the gas power input per unit volume and the superficial gas velocity as shown here. This is for a sparge system. Now, the superficial gas velocity can in turn be written as in the form of the volumetric gas flow rate and the diameter of the impeller square with some constant. So now again, the superficial gas velocity can be written in terms of Q and D as Q by D square. Now for scale up, we know that KLA is constant. Now for making KLA constant, now this PG by DQ can in turn be written in the form of the operating parameters N, D and the volumetric gas flow rate as shown earlier by this empirical correlationship as shown here in equation 3. So if you see equation 3, we have already derived how Pg by dq can be related to N, D and Q. So we can replace that correlation here so that the only variables we have now are N, D and Q. So this turns out to be N 7 by 2, D 7 by 2 by Q 1 by 4 multiplied by Q 2 by 3 by D 4 by 3. So this is constant, which is KLA. So at the two levels, prototype and the model type, the correlationship between all these three parameters at the model and the prototype can be given as shown here in this equation, where your N 7 by 2 at the prototype, your D, it goes minus 4 by 3. If you do 7 by 2 minus 4 by 3, then you become 20. It's 8. It's 13 by 6. And your Q becomes 2 by 3 minus 1 by 4. So again it will become 5 by 12. This at the prototype is equal to Nm 7 by 2, Dm 13 by 6 and Qm 5 by 12. This is what has been shown here in this equation, which I have underlined with a curly bracket. So if now we know the constant scale factor, then this is how the impeller speeds at the two scales can be related if KLA is the scale-up criteria.